So in this video, I'm going to continue our conversation about comparators, but it's going to be a little bit different than the example of a comparator that we saw in the previous video. What I want to talk to you about first is this idea of serial versus parallel arithmetic. So everything that we've seen so far, the adder, the subtractor, and the comparator from the previous videos, have been in parallel. And what that means is that I have the entire binary value coming in at the exact same time. So if I'm adding two binary values together, I have both of those binary values coming into the adder at the exact same time. Or if I'm comparing two binary values to determine if they're greater than or equal to one another, I have both of those entire binary values coming into the comparator at the exact same time, and then I compute the result. This is very nice. It's actually very fast to do things that way, but it won't always work out for us to do things like that. That's what's called a parallel form of arithmetic, when I actually have the entire thing and I can compute that addition in parallel, or I can compute that computation, that comparison in parallel. In other cases, the most prominent example being networking, right? My information is going to come in serially, meaning I will get one bit at a time from each value. So if I want to compare two values to determine if they're equal or not, I'm going to have to compare two bits one at a time, right? Until I don't get any more bits coming in from my input. This is what's known as serialization of values. So I no longer have access to all of the bits. I only get one bit at a time, and I have to determine a result. I have to piece together a result based off of the information that I have coming into me. This changes the designs of our circuits. This changes the way that our circuits operate. So let's take a look at how a serial comparator works. Again, just to reiterate one more time, in the previous comparator video, we saw what was called a parallel comparator. That took in the entire binary value at once. So if you looked at our 4-bit comparator, it took in two 4-bit binary values all at the same time. In this case, we're going to build a comparator, right, that's only going to be able to read in one binary value, one bit at a time. And so we're going to have to process many bits before we actually have our final answer. So let's take a look at what that might actually look like, right? Here are two binary values, 1011 and 1000. And I want to know, right, is this value greater than this one, less than this one, or equal to this one? But I can only see one bit at a time. So how is this actually going to work? I'm going to look at this first bit from both numbers, 1 and 1. I'll look at those and I say, hey, those are the same, right? Those are equal. So I'm going to assume that these values are equal. And then I'll look at the second bit from both values. I'll say those are both zeros. And so I'll look at those and I'll say, hey, those are the same, right? I'm going to continue with my assumption that these numbers are in fact equal. And then I'll look at this third bit from both numbers. So I have a 1 here and a 0 here. And now I look at these and I say, oh, wait, this is a 1 and this is a 0. So now A, this top number, must be greater than B. So I'm going to switch my assumption to say that A is greater than B. And now, regardless of what bits I feed in next, right, it does not matter what these bits are. I cannot be budged from this knowledge that A is greater than B. There is nothing that I could see that's going to change my opinion that A is greater than B at this particular point, right? The only way I could determine that these are equal is if, in fact, I check each one of these binary digits from both numbers, and they are, in fact, equivalent. But all it takes is for one mismatch for me to immediately know whether a value is greater than or less than, and then that fact doesn't change. It does not change based on any other information that might be coming in. So we could actually codify this up as a state machine. Here is a Mealy machine, right, where we start out assuming that things are equal. We're going to start out in this equal state, and as long as I see a 0 coming in from both digits, or a 1 coming in from both digits, right, I'm going to remain in this state. I'm going to remain in this state of equality and assume that this is in fact equal to one another. As soon as I see something that proves the contrary, right? As soon as I see something that proves something different, for example, I see that the input from A is 1 and the input from B is 0, that's going to then indicate that A is greater than B, and I cannot get out of this state. Once I am in this greater than state, there's no way for me to get out of it. A is now greater than B, and it always will be. It always will be. So there's nothing that I can do to get out of this state. There's nothing at all I can do to get out of this state, right? Same thing for less than. Same thing for less than. So if I see that A is less than B in one digit, then there's nothing that can change my mind. A will always and forever be less than B. The output of this Mealy machine is going to be the number, right, that is greater than or less, is going to be the number that is greater than, right? So it's going to be the maximum. We're actually using this circuit to find only strictly greater than, though it could easily be tweaked to find less than or equal to instead if we wanted to, right? In this particular case, we're finding strictly greater than. So what does that actually mean? If I look at the outputs here, right, when I'm assuming that they're equal, the output is just going to be whatever I'm seeing. If I'm seeing 1s, then I'm going to output a 1. If I'm seeing 0s, then I'm going to output a 0. As soon as I determine that A is greater, then I'm just going to output whatever the value is for A. So here I see that A is a 1, I'm going to output a 1. I see that A is a 0, I'm going to output a 0. Or A is a 1, I'm going to output a 1. If I determine that B is greater than A, then I'll just output whatever B is. So here I see that B is greater than A, I'll output a 1. If B is a 0, I'll output a 0. If B is a 1, I'll output a 1. So the output of this Mealy machine is simply the maximum. I give you two numbers, and it's going to always output the maximum value. So it's not an entire comparator per se. It's only computing one of those particular things. But you could very easily rework this Mealy machine to give you the smaller of two values, for example, the minimum, or only give you the values if they're in fact equal to one another. So it could be reworked for that purpose. But the reason why I like to go through this example is because based on this finite state machine, we can construct a two-way max finder, right? So I give you two binary values, and that's going to give me the largest of those two values, right? And I can actually use these two-way max finders to then find the maximum of any number of binary values that I could possibly imagine. So here you see I've got 3 of these max finders, and now I can find the maximum of 4 values if I want to. So I take the maximum of C and D, I take the maximum of A and B, and then I take the maximum of those two maximums, right, for example. I could rework this to take the minimums of these 4, just with a slight tweak to this Mealy machine here, right? Or I could include even more values. I could find the maximum of 8 values or 16 values using a very similar setup to what we see here. So again, the primary difference is that the way that this comparator works, the way that this max finder works, is in serial. It's reading things in 1 bit at a time, exactly 1 bit at a time. It does not know the entire binary value at the beginning. It only knows 1 bit at a time. And the reason for that, again, like I said, is because we won't always know the binary value ahead of time. We won't always know the entire binary value ahead of time. We may only receive it in bits and pieces. We may not know how big our binary value is. What if in some cases I'm dealing with binary values that are 32 bits wide, and then I need to adapt to 64-bit binary values? This serial comparator can handle either case. Whereas if I give you a 32-bit comparator, then I cannot crunch 64 bits through that comparator. It can only fit 32. So by doing things in serial, it may actually take a little bit longer, right? It's not going to be as fast, but it does give you more flexibility and allows you to perform some different kinds of operations that you may not otherwise be able to perform by doing things in parallel.